So 7.3 is multiplication of radical expressions. So this first example here just kind of show us that, hey, what can we do when we have two radical multiplying together? This first approach here, what we did here, suppose we don't know how to multiply a radical expression, but we do know how to simplify it, meaning we can take the radical of 4 and we get 2, and then radical square root of 25 we get 5, and then we multiply the result. So this is following the order operation, and that give us 10. Now, if we try to do something new and say, okay, well, what if I don't want to take the square root individual? What if I want to times the radicants and square root the result? Would I get the same answer? And the answer is yes. We can take the radicand and then multiply them first, and we get 100 in the radicand, and then take the square root of that and give us the same answer. So this is not always true. It's only true when we have the index matching. So you have indexes 2 there. So that's the rule with multiplication radical. We can multiply radicals and then take the radicands, multiply them, and then square root at the end or end root, as long as the two radical terms have the same index, right? So this means same index, right? If they're the same index, we multiply radicands, and then simplify afterward, or take the square afterwards. In 7.2, we also learn rational exponent form from radical form. So n root of a and n root of b is the same thing as a to the 1 power of a to the power 1 of n, and then b n root of b is something as b to the power of 1 over n. That should be an n there. And then when we multiply them, we can just say, okay, that's the same thing as a times b to the same power 1 of n. That's using property of exponents there. So that's what this lesson is. So you multiply two radical expressions and make sure the index is the same. So here's some example here, right? We got radical 3 times radical 7, the index matching. So to finish the problem here, we'll just say, well, that's just 3 times 7 inside. So we get radical 21. 21 is not a perfect square number, so this is as far as we can go, leaving an exact answer. Over here, square root of x plus 4 times square root of x minus 4. Since the index matching, we just take the radicands and multiply them. So we get x plus 4 times x minus 4. That turns out to be a difference of square. Notice that this does not mean, okay, I'll just write it in red. So some student will just overlook this. Well, can I just do this here? The answer is no. This is not allowed because we don't have a rule for square root of a difference becomes the difference of square root. That's not a rule. That's just something that we intuitively think that is correct, but it's not correct. The rule we're looking at in this section is if it is multiplication inside the radical, then we can split the radical into two separate radicals, but it's not the same thing with subtractions or additions. So this is as far as we can go there. Okay. Let's see here. What do we got? Cube root of 4 and cube root of 6. The index is matching for both radical, so we can just multiply the 4 and the 6, and that becomes the cube root of 24. Now you may think, okay, well, cube root of 24. 24 is not a perfect square. Perfect cube. But it contains a perfect cube factor, right? So the way we do that is in the next lesson, the next example here, I'm going to show you how to do that here, but let me just kind of give you a breakdown of this one here. So 24 is not perfect cube, but we can extract a perfect cube factor from that. We can rewrite 24 as 8 times 3, right? 8 is a perfect cube number, and then use the rule of radical multiplication. We can split this into cube root of 8 times cube root of 3. Cube root of 8 now become 2 times cube root of 3. So that is our answer. So individually, we can't really simplify them, but if we combine the radicands, we can get that product to this form here. Okay. Here's some more problems for us to simplify using multiplication of radical. 200 is not a perfect square number. So there's no single number that when we square to get 200, but 200 contains a perfect square factors, and you're probably thinking that's 100. So that's what we're doing here. To simplify this type of radical, we rewrite the radicand as a product where one of the factor or more than one of the factor contains the perfect square factor. Sometimes it's easy to go straight to the biggest perfect square number. Sometimes it's not. So you just have to do a lot to get good at it. So we get 10 root 2, right? So 10 root 2 is the answer for square root of 200, the simplifying answer. It gets a little more confusing when we look at variable at the same time. So when we get to this here, we have the coefficient, and then we also have the variables. So the easiest way is separate the coefficient from the variable. So you can do this here. I'm going to write this a little bit longer than it should. Once we get good at this here, I'm going to do this really quick. I'm sure you guys you can do this in your head here. But the first thing is to do this and say, okay, do each of this variable of coefficient simplify. We know that 18 can be simplified under the square root, so that's 9 times 2. And then x cubed, we can look at that as x squared times x, and then leave this alone. The reason why we're looking at perfect square because it's square root. If it's cube root, then we're looking at perfect cube factor within the radical. So square of 9, if we separate square 9 from the 2, that becomes 3, so that would be 3 root 2 for the first thing. And then over here, if we assume the variable is all positive, the square root of x squared is going to be x, and then there's one x underneath the radical, and then square root of y. Now combine all the radicands together, and then multiply the coefficient. That leaves us 3x square root of 2xy. That's the answer. Okay. Now I'm just writing all this step down so that way you can see what you can do to start out. But once we get good at this, you probably can do a lot of this work just like you can condense these 3 steps to just 1 or 2 steps then to get the answer. And that's the thing with radical is that once you see it, you know what you're doing. But if you have a hard time seeing what's going on, you can totally go off the tangent and get a totally different answer. Here's another example. Cube root of negative 72. So with odd index, we're allowed to simplify negative radicands. Okay, so that's allowed. If even is not allowed. Okay, so let's do this. So 72 is negative 72, and it's cube root. So to simplify this cube root, we want to find a perfect cube factor within negative 72. Okay, so can someone give me a breakdown of negative 72 such that we can simplify a perfect cube factor from it?
9 into 8.
9
into 8. 8.
8.
9 multiply 8. Yeah.
So 9, 8 will work, but there's a negative, and what we want to do is decide, where do we put the negative, because it's cube root. Okay, so that means we want to simplify the perfect cube factor, which is the 8 there. So if we do that, we allow to take the cube root of a negative number. So we want to put the negative in front of 8. So that allows us to pull out the negative 2 and leaving the 9 inside, because we don't want to leave the negative inside. Okay. So that becomes cube root of negative 8 times cube root of 9. So that's negative 2 times cube root of 9. So that's the answer. Another thing comes up too as you do this, and to the point where the index become very confusing, and you want to make things simple by treating the index, all index are square root, which is not true. So you want to pay attention to that. When you write the index, clearly state that so that way it remind you, okay, am I taking the square root, the cube root, the fourth root, or something else? So this right here doesn't simplify anymore because it's cube root of 9. It's not square root of 9, right? Square root of 9 is 3, cube root of 9 is not 3. So pay attention to the index so that way you don't confuse it with another index. Let's look at this one, 162 x to the 6, and we're taking the fourth root of that. So if the index is the fourth, is 4, meaning the fourth root, we're trying to find factors within 162 that perfectly fourth rooted, meaning, you know, I'm running out of words to say. So there's perfect square, perfect cube, and then perfect quad. I don't know if that's the actual name for it, but that's the goal. Is can we find 4 factors that multiply together within 162, so we can take the fourth root of that and we can simplify. The x to the 6, that's the easy one because we can just do x to the 4th and x squared, and that give us x to the 6th. But 162 is kind of hard to see that right off the start, so you just have to do some work there. What you can do is you can take 162 and break that down, you know, if you want to. That, you know, maybe that's easier to find out. So 81. So I got 2 times 81, and then if your times table is good, you can see right away 81. Do you think 81 is a perfect quad number there?
3.
3 what?
3 is quad for 81.
3 raised to the 4th power, right?
Yeah.
That's 3, 3, 3. So that's what we have there. So we can rewrite the fourth root of 162 x to the 6s, 81, right, times 2, right, and then x to the 4th and x squared. And the fourth root of 81, if you get really good at this here, you can just go straight to simplifying each term without rewriting them separately. You can say the fourth root of 81, that's going to be 3. And then the fourth root of x to the 4, that's going to be x. And then everything else kind of stay inside, right? So 81 comes out at 3, and that comes out. So we're looking at 3x times the fourth root of 2x squared. And that should be the simplified answer. All right. Any questions so far in this example here, guys? Multiplying of radical expression and simplifying it. Here's another one here's a good couple ones actually. There's a couple more ones down here. I'll let you guys work on this one here. Okay. So this is a cube root of 16. Square root of 16 is 4, but cube root of 16 is not 4. So what do we need to do? 16 is what times what? 16 is
8 into 2.
Yep, 8 times 2. Now let me show you guys a much better way to simplify the variables with different power. Okay, so it's gonna take a minute here. So first of all, let's simplify the cube root of 8 first. Okay, so that's gonna be 2. Okay, all right. Here we go. All right, so 3 divided into 7 is how many times? 3 divided into 7? How many times 3 goes to 7? 2. What's the remainder, Javier? 1, right?
Yeah.
So that means there is 1 power of a inside. Next, How many times 3 going to 14? 4. So b to the 4th. So 3 going to 14. 4 times, that's 12. Remainder is 2. So there's b squared inside. And that's the answer. So you can sort of do that with the variables that contain powers greater than the index. So instead of doing what I did up here, rewrite like this form, you can actually divide the index into the powers and then leave the remaining powers inside and then bring out the actual the powers that divides into 7, 14 outside. And that's pretty much it. I mean, that's how you simplify a radical expression that contain fractions, not fractions, coefficients and power. Yeah. All right. Some problems you have to multiply first and then simplify, like this one here. See how individual 15 and 6 doesn't really, the square 15 and square 6 doesn't really quite simplify yet. But if we multiply the two radicands, we get 15 times 6, I think that's 90. And you can simplify from there because now square 90 contain the perfect square factor, and that is 9. And then now become 3 root 10, right? So some problem you ask to multiply the radicand first and then simplify, right? So keep that in mind. If individually it doesn't simplify as much, you want to multiply the radicands and then pay attention to the index or the index matching before you multiply. So this is 7.3, 7.4. I think there's division and adding, subtracting. With adding, subtracting, the rule is slightly different. Is the requirement is more than just multiplication. Multiplication, as long as the index is same, we can multiply the radicands. With adding, subtracting, there's two requirements. You gotta have matching index, and then you also have to have matching radicands. So that's gonna be in 7.4. Okay.